Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. We are from Group 7 and we are here to present about the assignment 1, which is the topic of fuzzy logic speed control of permanent magnet, synchronous machine, and feedback voltage ripple reduction in flux weakening operation region. So this is our group member. First we have Nurin, Zawanah, me myself, Wafiyuddin bin Fathulmu'en, and then Mohamad Arif Farhan.
There are many research works are ongoing to secure and optimize the operation of synchronized machine. Here, we discuss the following items from the research, which consists of introduction, findings, methodology, and critical analysis. Introduction of the research. First, the overview of the study. The study focused on voltage feedback flux weakening control for non-salient PMSM, which is permanent magnet synchronous machine. It addresses challenges in the flux weakening region where machines operate beyond their base speed. The issue identification. It analyzes steady-state feedback voltage ripple in flux weakening, highlighting problems caused by current common ripple. It recognizes the significant issues for systems with high inertia, leading to performance deterioration and potential oscillations. It proposed solution which introduced an adaptive fuzzy logic controller (FLC) for speed control. It aims for fast speed dynamics and reduced steady-state ripple, especially in the flux weakening region. The key findings in the study is the adaptive FLC achieved better performance utilizing DC link voltage more effectively and enhances overall efficiency and extends the operating range of non-salient PMSM. Methodology adopted to solve the problem of the research paper. The researchers applied a combination of modeling, simulations, and experiments to address the problem statement. Permanent magnet synchronous machine (PMSM) in the synchronized reference frame. This model was used to analyze the feedback voltage ripple induced by the current, common ripple, and its impact on system performance in the flux weakening region. Simulations were conducted to analyze the steady-state feedback voltage ripples in the flux weakening region and to evaluate the voltage disturbances induced by the Q-axis current common ripple and the speed ripple. The researchers also used linear rise block diagrams and transfer functions to analyze the voltage slope and the impact of voltage disturbances. So here we can see the two results of the simulation. Next experiment. Experiment 1. The experiment analyzed the performance and characteristics of a control system implemented on the D-space platform using a non-salient PMSM. The experiment aimed to analyze the performance of the control system under various conditions, focusing on speed and torque ripples and their sources within the experimental setup. Additionally, the study involved the design and the implementation of an adaptive FLC. This controller was compared with a conventional speed PI proportional integral controller through experiments in both constant torque and different flux weakening regions. The right figure shows a block diagram of two inputs and one output FLC combined with a scaling factor at the output. The general FLC is mainly composed of four components, which is fuzzification, fuzzy rule base, inference, and defuzzification. The experimental results were used to verify the performance of the adaptive FLC in reducing feedback voltage ripple and improving system performance. This figure shows the membership functions of the input and output adopted according to the experimental results. The membership function mapped the CRISP value of the inputs and output to the membership degree micro of each fuzzy set, as shown in figure A, and B. The triangular membership functions are used for the input En and E.N due to their high computational efficiency. The singleton membership function is used for output variable U as shown in figure C. This experiment is mainly used for fuzzification component. Next, experiment 3. The experiment aims to understand and compare the behavior of feedback signals under different operating conditions, which is case 1 and case 2. The focus is on identifying and analyzing ripples in feedback voltage and currents, particularly in mode B. The influence of load torque on the feedback voltage ripple is explored, with specific attention to its impact in the small q-axis voltage region. It can be seen that in case 1, as shown in figure A, the ripples of the feedback voltage and current are quite small in both modes A and B. However, in case 2, as shown in figure B, the ripples in feedback voltage and current are more apparent than those in case 1, which are mainly in mode B. In addition, it can be seen that the feedback voltage ripple becomes higher in smaller q-axis voltage region when the load torque increases, which is consistent with the analysis. Overall, these researchers applied a comprehensive approach that combined mathematical modeling, simulation, and experimental validation to address the problem statement and evaluate the effectiveness of the adaptive FLC.
Next, we move on to the main finding of this research paper. First, the speed ripple in the flux weakening control strategy can be induced by both the speed sensor and the voltage ripple caused by the Q-axis current command ripple. Next, the voltage ripple in mode B, flux weakening region, tends to be higher than that in mode A, which is constant torque region, especially in system with large inertia and small torque constant. Next, the feedback voltage and current ripple are more apparent in mode B compared to mode A, especially in small Q-axis voltage regions when the load torque increase. The coefficient kVA and kVB, which represent the voltage ripple in mode A and mode B respectively, are almost equal to 1. You can see in the figure beside. The bandwidth in mode A remain constant, while the bandwidth in mode B becomes smaller in the lower Q-axis voltage region, which is in the figure 7. And lastly, the predicted voltage ripple based on the analysis does not perfectly match the actual result due to the approximation, the neglect of resistance, and the limitation of the linearized small signal model. So the actual value may not be accurate with the experimental value because the neglect of the resistance and the limitation in linearized small signal model. The key takeaway that has been taken from the research paper is first, the speed ripple in a flux weakening control strategy can be influenced by various factors, including speed sensors and voltage ripple. The voltage ripple in mode B, flux weakening region, tends to be higher and more apparent than in mode A, which is in the figure beside. Mode B is higher than the mode A. I'm sorry. The analysis of voltage ripple in the flux weakening region is based on approximation and linearized model, which may not perfectly match equal actual result. The finding provide insight into the behavior of voltage and speed ripple in different operating mode, which can be valuable for the design and optimization of flux weakening control strategies in electric drive system. So what can we conclude from this research paper is first, the paper analyzed the feedback voltage ripple in the flux weakening region in a speed control system. Second, increased feedback voltage ripple caused by current command ripple can negatively impact system performance, particularly in the flux weakening region. Reducing the bandwidth of the speed loop can decrease current command ripple, but hinder speed dynamic performance. Fourth, the an adaptive FSC, which is fuzzy logic controller, then is proposed to address this conflict and is compared to a conventional proportional integral PI controller in constant torque and flux weakening regions. Fifth, experimental results demonstrate that the adaptive FLC fuzzy logic controller achieve good dynamic and steady state performance in different operation regions. The adaptive FRC fuzzy logic controller has also reduced feedback voltage ripple, allowing for increased DC link voltage utilization and flux weakening capability. However, the adaptive FRC that introduce additional parameter that require proper tuning, increased complexity and tuning effort will be more difficult to control. The and lastly, the improved performance of the FLC come at the expense of complexity and tuning effort, which is more complicated but will be more accurate.
Now moving on to the critical analysis of the research paper, we first look at the strengths. The research paper provides a detailed analysis of the steady-state feedback voltage ripple in the flux weakening region of the permanent magnet synchronous machine. It proposed an adaptive fuzzy logic speed controller which can obtain both low current ripple and high load torque disturbance rejection capability in the flux weakening region. The figures below shows the speed dynamic performance under a load disturbance when the machine is controlled at 800 rpm in the flux weakening region. In figure A, case 1, we can see that the current ripple is much smaller than that of case 2, figure B. But the machine in case 1 still has much longer recovery time against the load torque disturbance. However, with an adaptive fuzzy logic, as shown in figure C, both low current ripple and high load torque disturbance rejection capability can be obtained. Next, we dive into the limitations of the study. Since approximations are used and resistance is ignored in the analysis, the actual value of the voltage ripple differed from the prediction. We can see this in the graph of spectra of the speed ripple, where the actual voltage ripple is much higher than that of the predicted voltage ripple for all three cases, especially in the figure B. Other than that, the research focused on non-salient permanent magnet synchronous machine, and the findings may not directly apply to other types of machines such as salient PMSM or DC motor. Uh, Lastly, the experiments are implemented only in the constant torque region, and the findings may not be applicable in different operating conditions such as variable load condition or even power supply variation. Lastly, in critical analysis, implications of the study. In my opinion, this study have various significance, especially in electric vehicle industry, since the PMSM is often used as traction motors. In the study, we have learned that the reduction of feedback voltage ripple in flux weakening operations contributes to smoother operation at high speeds, which can help to improve the electric vehicle efficiency due to the smoother operation. Uh, Also, efficient control of the PMSM through fuzzy logic can lead to a better energy management, which can help to extend the electric vehicle driving range. This can be achieved by optimizing power delivery to wheel and minimizing energy losses in motor control system. Now for the potential future direction of the study. Since the study only focus on one type of machine that is non-salient PMSM, by investigating the performance of the proposed controller in different type of PMSM such as a salient PMSM or fractional slot concentrated windings, it can help to broaden the use of fuzzy logic controller. Uh, Other than that, by extending the experimental evaluation to include a wider range of operating conditions and load variations can also help to develop further the usage of fuzzy logic controller in reducing the voltage ripple in flux weakening operation.